Hello everybody, it's Mrs. Pound and I'm back with another video from Chapter 2 about the chemistry of life from BJU Biology 4th edition. We have been talking about basic chemistry from Section 2A, and today our focus is going to be on solutions. So our objectives for today are going to be to define solution, solvent, and solute, list the important molecular characteristics of water, differentiate between diffusion and osmosis, and explain the difference between acids and bases. First thing I want to talk about is a homogeneous mixture. This is a mixture that is the same throughout, like sugar water. If we add sugar to water, it's going to dissolve the sugar and it's just going to look the same. It's really just going to look like water, so it looks the same throughout. A homogeneous mixture or homogeneous mixture is also called a solution. So down here we have some pop, and that is also an example of a homogeneous mixture because it's the same throughout. Now, in a homogeneous mixture, we have something called the solute. This is the substance that is dissolved. So in our sugar water example, the sugar is the solute. It's the stuff that is dissolved. The solvent is the substance that does the dissolving. In our example, that is water. So in sugar water, the solute is sugar, the solvent is water. Now, one rule really for this is that the lesser of the two substances is the solute, and the one that is in greater abundance is in the solvent. This rule you can use like if you were making a solution of two liquids, then you would go with the solute is the lesser amount and the solvent is the greater amount. Now, we call water the universal solvent because it dissolves a lot of things, and there's a special reason that water dissolves a lot of things. This is because the forces of attraction between water molecules that give water some of its unique properties are hydrogen bonds. Because it forms these hydrogen bonds with a lot of substances, it is able to dissolve a lot of things. These hydrogen bonds also cause water to stick to things. That's why when you get wet, water sticks to you. And it also causes water to, and we call that adhesion. It also causes water to stick to itself, which we call cohesion. That's why we can pour water in a nice stream or it forms drops like in the background picture. Something else we have to talk about with uh, homogeneous mixtures or solutions are concentration. This is the ratio of the solute and the solvent. So here we see somebody adding milk or cream to some coffee. And so that is changing the concentration as they add more solute to the solvent, okay? It's becoming more concentrated. So for our example of sugar water, the more sugar we add to the water, the more concentrated the solution is, the more sugar there is in that solution. So if you add just a little bit, it's not very concentrated. If you add a lot, it's very concentrated. Another thing, a special kind of solution is an acid. This is where you have an abundance of H positive ions. Remember, this would be a hydrogen atom that has lost its electron. Okay, and acids tend to taste sour. That's one of their characteristics, but acids have a lot of hydrogen ions in them. Bases have an abundance of OH negative. Okay, um, OH negative, they have lost uh, hydrogen proton, or excuse me, hydrogen ion. And so we have OH negative, and bases tend to taste bitter. Now, when we put together an acid and a base, they neutralize each other, forming water and salt. So if you're performing a neutralization reaction, you're going to get salt water, essentially. But if you're doing this with a strong acid and base, don't drink it. because you might have your concentrations off. If you had it perfect, it should be fine, but if you have it just a little bit off, it can be dangerous. Now, acids and bases in your body, having too high or too low can be bad. So you actually have what are called buffers in your blood that control acids and bases. And what these buffers do is they, depending on whether it's too acidic or too basic, they can absorb the extra ions and take them out of your blood to keep your blood in balance. So that is a buffer. They tend to neutralize acids and bases, and they can work with either one to keep an even pH in your blood. Okay. Another type of mixture that we talk about is a suspension. This is a liquid mixture in which particles settle out. So, like this mud puddle, if we stir up the mud in the mud puddle, it'll get really cloudy. But after a while, if you let it sit and you don't disturb it, it will settle out. So, that is a suspension. Different than a homogeneous mixture, because in a homogeneous mixture, there is no settling. There are also things called colloids, and these can be in sol or gel state. And I have an example of a jellyfish back here because it's kind of not completely see-through. That tends to be what colloids are like. Another example of a colloid is milk. So if you shine light on it, you don't see through it. It will reflect the light back at you, where a homogeneous mixture will not do that. A homogeneous mixture will not do that. Now, they come in a sol and a gel state. Now, a sol is a little more fluid, okay, moves a little around a little bit more. A gel is more like gelatin. And I use the example of the jellyfish here because our cytoplasm in our cells, which is the liquid part of our cells, goes in between these two states. Our cytoplasm is a colloid, and it will be more fluid sometimes and more gel-like at other times. Now let's talk about diffusion. So we're done with our solutions and our different mixtures. Let's talk about diffusion. This is the net movement of molecules from an area of higher concentration of a substance to an area of lower concentration of that substance. So here in the background, it looks like maybe we have some food coloring of some kind of dye. And a drop of dye was put in water, and now it is spreading out. It is diffusing throughout the water. So this is movement of molecules basically in a liquid, in a fluid, I should say, because this will also happen in a room. An example is ammonia. If I were to open a bottle of ammonia in the room, um, it would start out smelling very strongly by the bottle and eventually spread out through the whole room, and everybody would smell that ammonia. And that happens with a lot of smells, as you know. They will spread out. I'm thinking things like skunk, okay, and all sorts of things. And it will spread out, things will diffuse until the concentrations are equal throughout, then diffusion stops. So if there was some food coloring added to these bottles, it looks like it's reached equilibrium because there are no darker or lighter spots. And so diffusion has stopped. These are in equilibrium. And you've seen this if you add food coloring to water, it spreads out and spreads out and spreads out until the whole water is the same color. So it's reached equilibrium. Now, there's something called a concentration gradient. This is the difference between the numbers of one type of molecule in two adjacent areas. So I realize this is more of the sky, but let's pretend this is a solution in which I put blue dye on the right-hand side. Okay, so there's a higher concentration of blue dye over here, and it's spreading to the left where there is a lower concentration. There is a concentration gradient between the two areas. It's almost like a hill, where the dark color is at the top of the hill, the light color is at the bottom of the hill. So it's moving from where it's dark to where it's light. That is what the concentration gradient is like. It's going to go from highly concentrated to less concentrated until it reaches equilibrium and everything is equal in there. Now, when diffusion pressure is high, the material is far from equilibrium. So, kind of like, well, let's pretend my hand is a water pipe, like the water pipe in the background. If my water pipe is like this, I have a lot of pressure from water coming through that tube, right? And so it's really far from equilibrium because I have a lot of pressure here. If I even that out, like in my diffusion example, my concentration gradient evens out, I have less diffusion pressure, just like I would have less of flow of water through that pipe, and I'm closer to equilibrium because my gradient is not that great. So high gradient, high diffusion pressure, far from equilibrium. Low gradient, low diffusion pressure, excuse me, close to equilibrium. When we're talking about diffusion, we also talk about permeable membranes. These allow passage of all molecules through them. So just like these rocks, if you were to pour water over these rocks, the water will go through. That is permeable, and it's allowing all of that water through. We also have what are called semi-permeable membranes. These permit only certain materials to pass through, a lot like a colander, okay? And what makes this colander semi-permeable, or we even call this selectively permeable, are the holes. Anything too big will not go through the holes. And our cell membranes are really like this. And this is important for the process of osmosis. This is a special type of diffusion where only water is diffused through a selectively permeable membrane. So it only allows water to go in and out, not other materials. So if water goes in, okay, that cell will swell, and if it leaves, that cell will shrink. So some differences between osmosis and diffusion. First, diffusion can involve any molecule whatsoever. Ammonia, the stinky chemical from skunks, right? Um, anything, food coloring, okay, all kinds of things. Osmosis involves water only. That's the only thing it involves. Diffusion can happen anywhere. It can happen in this room, it can happen in a beaker of water. Osmosis requires a selectively permeable membrane, as we're going to work with in class. So our objectives today were to define solution, solvent, and solute, list the important molecular characteristics of water, differentiate between diffusion and osmosis, and explain the difference between acids and bases. Don't forget your 5 questions and remember to keep watching this video to answer the questions at the end.